So now we're going to expand our description of motion into more than one dimension, into 3 dimensions. In order to do that, we have to talk about the concept of vectors. So if you're not familiar with vectors, I'm going to run through a couple of simple examples of how vectors are used to describe quantities that have magnitudes and directions. So let's start off with a simple coordinate system. So here's an x and y axis. And if I want to define a point on this axis, I could draw a point here, and I could say that its Cartesian coordinates are x comma y. That specifies the distance along the x-axis where the point is, and the distance along the y-axis where the point is, and so that specifies this point. I could equally well say that this point is a distance r from the origin, where in fact r is equal to the square root of x squared plus y squared. And if I wanted to define the complete location of that point, I would have to introduce an angle, theta, say measured from the x-axis up to r. And so now you can see that if I drop a perpendicular here, this is a right triangle. And so I can say that the x component is equal to r cosine of the angle, and the y component is equal to r sine of the angle. And so I could equally well have written, instead of x comma y here, I could equally well have written r cosine theta comma r sine theta to describe the location of this point. So this is just a change of coordinates in some sense. We haven't really done vectors yet. But this is sort of setting us up to think about distances from a given point and the direction. So you can see as if I move theta around here, I can keep a constant r, and I would sweep out an arc in the xy plane, which would be the location of the points. And so we're going to then transition from talking about Cartesian positions and locations to something more akin to polar coordinates, or distances, magnitudes, and directions.